So it's really great to be back here and to be able to be representing the U.S. contribution to Ariel. And I'm really excited to help make Ariel a fantastic mission. I know it will. So I'm going to tell you a little bit about what CASE is, and we're going to talk about both the hardware contribution and some of the science. The science story for Ariel is an amazing story. And to help tell that amazing story, I'm featuring some art from the high school in Southern California. It's right down the road from JPL, so you'll be seeing some of their art. So the landscape for CASE is that we were selected conditionally during an NASA Explorer program call. We were in the mission of opportunity category. That conditional selection was in July of 2017. But of course, conditional selection and selected for implementation aren't exactly the same thing. So our implementation decision came last month. So we're very happy about this. Of course, CASE is a way for NASA to participate in studying the atmospheres of planets that either have been found with Kepler or are going to be found with TESS. So it's a great way to leverage some of NASA's science investments in the exoplanet area. My outline's pretty short. We're going to talk about the CASE science requirements, the CASE hardware delivery, and then kind of a little bit of the broader scope of Ariel science. Now that story really starts with kind of the big picture questions that everybody can connect to. That's one of the beautiful things I love about the Ariel mission. These are questions that can only be answered by a large-scale statistical survey of exoplanet atmospheres. They're questions like how do planets form, what are they made of, how do their atmospheres evolve. And again, the universal appeal of this mission is that everybody understands these questions and finds them compelling. Now, the data set that Ariel is going to measure can go in many different directions, and there's really no time to do that justice, but the pinwheel plot on the left there is supposed to show just some of the different science directions that can be addressed with the transmission and emission spectroscopy with broad simultaneous spectral coverage that Ariel will have, whether that's planet formation or atmospheric evolution, atmospheric chemistry, global climate. This is a foundational data set that this mission will produce during its lifetime. And that data set is going to connect the fields of astrophysics and planetary science. It also has a very important role with JWST. JWST will do exquisite observations of exoplanets, but it will have a much more limited sample than Ariel. You can think of JWST as a zoom lens to really zoom in and look in detail at select exoplanet atmospheres. What Ariel is going to do is complement that. Kind of the wide angle lens to really show how those detailed measurements of things what we make will fit into the broader exoplanet. In this slide, I'm showing you a figure that was in our CASE proposal that really shows where the CASE detectors, which shows where the CASE detectors and the photons that the CASE contribution will measure fit into the overall Ariel transit and emission spectroscopy measurements. So the CASE detectors measure short wavelengths of light. There are 3 photometric channels and 1 spectroscopic channel. All this is between 0.5 and 2 microns. Now, what this simulation that I'm showing here illustrates is that for a typical hot Jupiter atmosphere, it's hard at long wavelengths to tell the difference between an atmosphere that's clear and one that's cloudy and one that has hazes. But these differences show up at short wavelengths. This naturally led to determining the CASE science objectives. It was the sensitivity to certain kinds of effects that happen at short wavelengths. So we have 2 major CASE objectives. One is to determine the aerosol occurrence rate. And these are connected to our level 1 requirements. And the other is measure the geometric albedo of exoplanet atmospheres to constrain aerosol composition. So part of what we'll be doing in the CASE project is providing aerosol and albedo data products based on analyzing those data. Now, in the NASA formalism, we have a science traceability matrix that's driven by science requirements, and we estimate our margin against those requirements. I'm very happy to say that for our two key science parameters, the aerosol slope precision measurement and the albedo precision requirement, we've done some design reference mission simulations using our best approximation of the Ariel instrument model, circular yellow book, and an observing model and a target model. And what we find is that we meet those requirements with a lot of margin. Margins are right up here, 300 to 400%. So that's a very good thing from a science perspective. We are certain we're going to get great science with this mission. Now, of course, this is just a small slice of some of the science that Ariel will do. We'll come back and talk about that more. At this point, I'll turn to the payload a little bit and show where the case hardware contribution fits in. We're contributing to the fine guidance system, which sits back here on the back of the optic extension back of the Ariel telescope. And again, we have these three photometric channels and one spectroscopic channel, which are the wavelengths of light recorded by the case detectors. The actual hardware is a pair of detectors in their package assemblies, printed ink cables, cold front-end readout electronics, one of those for each detector. That's all housed in an enclosure, which also includes a thermal management system, because the detectors and cold front-end electronics have some specific temperature requirements. All this is Euclid heritage. So we're leveraging the investment that was made in Euclid. We're operating the hardware the same way. So we're very confident in being able to deliver on time and meeting this. Another view of the case hardware. Here I'm showing you some more detailed images of the detector and cold front-end electronics, kind of a top view of how the cold front-end electronics box sits close to the fine guidance system where our detectors plug into that. Now, one of the things I was personally very pleased about was that last year the National Academy of Science released this consensus study report on exoplanet science study in the U.S. They mentioned Ariel in the case participation. I'll just draw your attention to two quotes from this exoplanet science strategy document, which is available on the web. The first is that the U.S. exoplanet community would benefit from participation in Ariel, and the second is that U.S. scientists would benefit from the case mission by participating in the planning, execution, and exploitation of the Ariel survey. So I was, of course, really happy to see that this was recognized. The rest of the science team was thrilled, and we're convinced the case is a fabulous opportunity for the U.S. science community. Now, I want to turn to some kind of beyond case work that we've done in the case science team. This is a design reference mission simulation where we were trying to answer the question, what could we learn about planet formation with Ariel based on just the Tier 1 survey? I'm going to say that again, based on just the Tier 1 survey. So we made a synthetic target sample. This is based on samples that predict test yields organized by real planets. And you can see the sample there. And then we used a target model reflecting kind of the yellow book Tier 1, Tier 2, and Tier 3 types of observations. And then just for Tier 1, we looked at the parameters that parameterize the so-called mass-metallicity relationship, which is a relationship of the extent of metals in exoplanet atmospheres as a function of planet mass. It's one of the key predictions of planet formation. The slope of this relationship, the scatter about it, the location of a breakpoint, or if a breakpoint exists in that curve, are all critical model-dependent parameters. So measurements of those parameters powerfully constrain planet formation models. This is all captured in a paper by Zellendal, 2019. But what we found is that for a Tier 1 survey, Ariel will do an absolutely beautiful job of constraining the mass-metallicity relationship. So, I mean, just the Tier 1 survey is really going to be a science treasure trove. Another area that we're looking at in the case science team is the potential for looking at smaller planets. So in this case, I'm highlighting a couple of recent findings. The large figure here on the right is a study of atmospheric evolution in planets that have a radii of less than 3 Earth radii. And it includes, these green triangles are sub-Neptunes, and these blue triangles are powerfully irradiated super-Earths, which are believed to have lost their original primordial hydrogen and helium envelope. I saw a slide earlier today, right after I came in, about the Fulton result showing the bimodal planet distribution or bimodal planetary occurrence rate for small planets. And that's connected to this idea that powerfully irradiated super-Earths can have their envelopes cooked off, and that's shown here in this model where the evolutionary tracks align with space. One of the interesting findings from this work, which is now in the archive and is publication led by Reza Estrella, is the finding that even the small sub-Neptunes go through significant atmospheric evolution and lose about 70% of their envelopes. So that really suggests something very exciting, which is that, at least for smaller planets, atmospheric evolution is something that's happening all the time, right? So we look at a small planet, it may have a low mean molecular weight atmosphere, it may be hydrogen dominated, and yet it has undergone significant evolution. And Ariel is going to give us a way to probe these atmospheres and look at the details of that go, they're completely transformative, that go far beyond what we can do in this sort of bulk composition type of analysis that we're limited to today. Now again, one of the things that I love about the Ariel mission is how easy it is to tell people about the science. Here's an activity with some 5th graders at a school in Santa Clarita, which is near JPL, and they're imagining an exoplanet in this activity. And really, I thought their art kind of captured this step into the unknown and this great adventure that Ariel is going to be scientifically for us. So I'm going to close with kind of just a listing of some of the CASE and Ariel benefits to NASA and the U.S. community. The CASE Ariel data will be used literally for decades to come. I think this is completely beyond a doubt. The CASE and Ariel results will be foundational for the emerging field of exoplanet atmospheres. I mean, you're talking about a mission that will produce a completely transformational data set. And this field of exoplanet atmospheres is the field in which the discovery of life outside of our solar system will be made. And I think finally, there's a legacy that Ariel will bring that goes far beyond the science, because it's really going to show us in this powerful statistical sense, for the first time, how our own solar system fits into the extended exoplanet family. So really, CASE is a historic opportunity for NASA and for the U.S. science community to participate in what is going to be an absolute great mission. Thank you.